Alright, let's get right into it. So you have gone through the theory, you have got the concepts down, but now you are standing there in front of the actual optical table. This is where the rubber really meets the road in ultrafast transient absorption spectroscopy or UTAS. We are officially leaving the textbook behind and getting into the real hands-on challenge of getting a clean usable signal. And this right here, this is the absolute fundamental truth of the entire field. It is a phrase every single experimentalist learns to live and breathe by. I mean, the quality of your amazing discovery, the clarity of your final results, it all boils down to how perfectly you can set up these tiny beams of light. You know the feeling, right? We have all been there. You run a scan, and the data that comes back is just messy. It's inconsistent, it's noisy.
It feels like it's not even there. It is, without a doubt, one of the biggest frustrations in the lab. So in this explainer, we are going to tackle the root cause of that problem head-on, the physical alignment of the system itself. And what's so wild is that this principle applies to everything. You could have the most cutting-edge semiconductor wafer, a brand new synthetic polymer, or even a delicate biological sample. But you know what? If your laser beams are misaligned, none of it matters. Your results will be completely useless. Alignment is and always will be the foundation everything else is built on. So where does it all begin? Well, every single UTAS experiment starts with one incredibly short femtosecond laser pulse. We take that single pulse and we use a beam splitter to create two totally separate paths. And this gives us the two main characters in our story, the pump and the probe. So let's talk about their jobs. The pump beam, that's the heavy hitter. It's a really high energy pulse that literally kicks the sample, shoving it up into an excited state. That kick also starts the clock for our whole experiment. Then you have the probe beam. It's much weaker. It basically acts as our eyes, showing up just a little bit later to see what happened and watch how the sample recovers and relaxes. Now, for our eyes to be really useful, they need to see a whole range of colors or wavelengths. And we do this by focusing that probe beam into a special nonlinear crystal, something like sapphire. This whole process generates what we call a white light supercontinuum. It's basically a beautiful rainbow pulse that gives us all that rich spectral information we're looking for. Okay, now for the ultra-fast part. How on earth do we measure things happening on femtosecond or picosecond timescales? You obviously can't use a regular stopwatch. No. Instead, we do something way cleverer. We actually turn physical distance into time. And this is the piece of hardware that makes it all possible. The delay stage. At its heart, it's a super high-precision mechanical track that the probe beam's mirrors are mounted on. By physically moving this stage back and forth, we change how far the probe light has to travel before it gets to the sample. And check this out. This is the magic conversion. Because the speed of light is a constant, moving that stage back by just a single millimeter delays the probe beam's arrival time by about 3.3 picoseconds. It's an absolutely brilliant way to film molecular dynamics with unbelievable precision, just by moving a mirror a tiny amount. But here's the catch. As that stage moves, sometimes over several centimeters, the beam has to stay pointed at the exact same spot. If you've ever run one of these experiments and seen your signal get all wavy or maybe fade out at those longer time delays, yep, that is almost always a sign that your beam is walking off the target as the stage moves. So how do we fix this? The secret, and I mean this is the essential motor skill for every ultra-fast spectroscopist, is a technique called walking the beam. This is truly the master key to getting a rock-solid, stable signal across your entire time scan. Let's just break it down real quick. You set up two irises, they're basically just little adjustable holes, pretty far apart from each other. You take the first mirror in your beam path and use it to steer the laser right through the center of the first iris. Then, you use the next mirror to steer the beam through the center of the second iris. You just go back and forth, rinse and repeat, until that beam zips perfectly through the center of both. And the whole point of doing this? Simple, really. The goal is to make absolutely sure that the laser beam is traveling perfectly straight and perfectly parallel to the surface of the optical table. This guarantees it won't wander off target no matter how far your delay stage has to move. All right, once the beams are traveling straight, there's one last absolutely critical check: spatial overlap. The pump and the probe beams have to hit the exact same spot on your sample. And we're talking about a target area that's often less than 100 microns across. That's smaller than the width of a human hair. You'll typically use a tiny pinhole or a fluorescent card just to make sure they are perfectly on top of each other. So you've done it. You've walked your beams, they're perfectly straight, your overlap is spot on, your signal is stable. You basically won half the battle. But here's the twist. What's so interesting is that even with a flawless physical alignment, your raw data is still not telling you the true story. Another challenge is waiting for you. That's right. After all that careful, meticulous work, the raw heat map of your data is still going to look distorted and kind of smeared out. The journey from that initial chaos to crystal clear data, well, it's not quite over yet. There's a subtle but critical optical effect that we still have to correct for. And that sneaky phenomenon is called Chirp. Remember that white light rainbow we made for our probe? Well, as it travels through all the glass optics, the different colors actually get separated in time. So the red light might get to the sample a little bit before the blue light does, or the other way around. This temporal smearing is what we call chirp, and it really distorts our data. So, the crucial point we'll leave you with is this question. Why on earth might the blue end of your spectrum appear to arrive later in time than the red end in your raw data? And, more importantly, how do you mathematically fix it to see the real picture? Don't worry, we are going to tackle that head-on in our next explainer.